Peter Corcoran is a professor and Vice Dean of Research and Graduate Studies in the College of Engineering and Informatics at NUI Galway. He is an IEEE Fellow with more than 450 technical publications, 85 plus peer-reviewed journal papers, 120 plus international peer-reviewed conference papers, co-innovator on 300 plus granted US patents, 80 plus granted European, with another 30 plus patents currently pending. He has numerous accomplishments, including former editor-in-chief of IEEE Consumer Electronics magazine till December 2016, completed 20 plus funded research projects, and managed 3M in research funding over the last 10 years. His research interests include smart imaging, advanced digital imaging solutions, biometrics for handheld and IoT devices, AI, deep learning and data augmentation and data generation, fog and mobile edge computing, internet tech and IoT, embedded edge AI. So today's topic is rise of neural accelerators, edge AI. So now Professor Peter can start the talk.
Okay, so you can see the slides there?
Yeah, we can see the slides.
So, in fact, the talk I originally said would be around smart cities. So I will cover neural accelerators later stage in the talk, but just to let you know that the focus is about smart cities. Now, if you look at the slide there, you'll see there's a short link, bit.ly link, and sometimes I will move fairly quick slides, so you may want to download these onto your mobile device. About 20 megabytes reduced form, and short link will give you a PDF copy. So thank you very much for the introduction and for the opportunity to talk at this event. So again, you can see a bit more about my sort of background here. But it's quite easy if you go and Google Scholar and search there, you'll find it fairly easily. Now, I'm going to talk about a few different topics today and how these trends will affect how we look on smart cities and how we design them. So, as we're a little bit late, I'll try to have time. The first part of my talk, I decided to reflect a little bit on smart cities and what actually are smart cities. And perhaps most importantly, as engineers, what do we want from the technology? So, if you think about a city from the top-down level, well, you begin. I did work 25 years ago on Internet of Things, but if you think in terms of the city, you think about infrastructure, you think about buildings in the city. You think about how these are connected together with power grids, transportation networks, possibly water and sanitation, but that's often a forgotten part of the infrastructure. And of course, all this is tied together by community networks, and as we'll shortly talk about that entity called cloud. We can also think of the city in terms of services. So ultimately, we're not just building infrastructure, but that infrastructure services to people. Transportation, commonly focused for the smart city. And of course, policing and security are also important. Then we have the less interesting aspects of a smart city, the security, the policing, response, and even less romantic, the maintenance, cleaning, and repair of the city. Now, I was going to suggest it might be good to turn up the microphone there. There may be some feedback. I can hear myself in the background faintly. Now, probably more important next week are the actual elements, the single elements, because these are the things where we can start our design. The vehicles, the different functions of factories, warehouses, transport hubs, and of course as we go down to our private homes, our mobile devices, and ultimately it's the people themselves that are the important parts of this infrastructure. Of course, most of us are electronic engineers or computer scientists, and so we ultimately think of the smart city in terms of the technology elements that we put together. And these, in a nutshell, these are the sensors and the actuators that will control different components of the smart city, the signal processing, and of course, for most of us, the vision of a smart city is about gathering all of the information from these, if you like, these sensing elements and control elements and gathering them up into a cloud infrastructure. Very likely these days applying artificial intelligence to analyze that data. So we can think of the smart city as a large collection of centralized data and the various control and logistical operations that we can manage using that data. Okay. Now, this is our first smart city, and it's very much cloud-centric in today's world. Okay. We think about the use of centralized big data. Of course, in the last few years, there's been a lot of public reaction against big data. And there's also a concern which certainly 5 or 6 years ago people didn't like to think about energy. Now today, energy and power consumption have become a very important part of the smart city. And so we'll talk about those shortly. But the key point here, and our first key point for today, is that today's smart city is very much enabled by cloud computing and big data technologies. Both of these are very much under public scrutiny, and so engineers need to take very responsible and transparent decisions going forward. And in this talk, we will look at some of the emerging trends and also some new technologies that can help to build a better smart city for the 2020s and beyond. Okay. Now, just to reflect on where we are today, I'll just give a quick history of ICT in the 2020s. In fact, I'll go back to the 1960s, but I'll go through this fairly quickly. So there was a time when computers were simple. In fact, you might argue for the first 4 or 5 decades of computing systems, everything was pretty straightforward. In the 60s, a computer took up a whole floor of a building, in some cases an entire building, and was managed by a large team of people. Then in the 1980s, we saw a revolution with personalized computers. But once we got into the 21st century, everything began to change very quickly. In the 2000s, people introduced virtual machines, and it became clear that a computer was in fact many computers. And this led then to the growth of the cloud. Data began to disappear into the network and into centralized repositories. Then in the second decade of the 21st century, our phones became very intelligent. And all of a sudden, they started to take over our lives and created the phenomenon we now call big data, where we are essentially sending more and more data and information up into the cloud. We're getting services in return and benefits, but these phones are very sophisticated, and I just show a system on chip there. Most phones now have quite sophisticated artificial intelligence engines inside the phone itself. So everything from the middle of that decade became about big data. And I think most of us will recall 5 or 6 years ago, we suddenly all got excited about all of the data that could be gathered. But of course, while we were doing that, a lot of corporations were developing advanced artificial intelligence engines and turning this data into new business models. And really, for the last decade or so, some of the biggest companies in the world have grown on data, and very much on personal data. They've been using this to drive their businesses, to anticipate and to basically access people. All of this changed in the last year and a half, 2 years, and I'm now going to talk a little bit about what I call the age of privacy and personal data security. And this is what's leading everything and driving everything as we move into the 2020s. It became a very abrupt reality check for the ICT industry. Now, just a personal reflection, in 2016, I published a paper in the World Forum for Internet of Things. This was in Washington, actually, in the US. And I received a fairly lukewarm reaction to this paper. At the presentation, people were kind of questioning if it was actually valid research. But my essential thesis was that we needed a privacy responsibility framework. And it was very important that this was applied in particular to the Internet of Things, where data has been gathered and more sophisticated data is being collected. So as I say, in 2016, people weren't very excited about this work. But then in 2018, this happened. The Observer, a very well-known and respected UK newspaper, broke the Cambridge Analytica scandal. And suddenly the public was aware, and was made very painfully aware, of what was happening, some of the things that were happening to all of this data, which was being gathered by large corporations. And as we all know, there has been tremendous backlash for this event. Big corporations have been forced to change how they do business. And perhaps most interestingly, regulators all over the world have begun to react quite aggressively against this behaviour. In Europe, we're very good at social responsibility. We're not so good at technology. And so we've taken a European approach and basically started fining large European corporations. And we've introduced something called the General Data Protection Regulations, which essentially make it very risky for large corporations now to work with people's data. So the fines now are in billions, and under GDPR, the potential fines are as much as 2% of global revenue, which is quite frightening for most companies. So our second key point for today is that in 2019, corporate reputations depend on how companies manage and protect their users' data. And this was something, as I say, that was of very little interest to people in 2016. Today, that has all changed. Now, I want to move away from privacy for a little bit and to talk about energy. And energy is something else that's come very much to the fore in the public eye. Climate change, we've just seen the latest climate change talks have finished with quite unsatisfactory results for many people. So I want to wind back the clock 5-6 years and talk about some research I did in 2013. I originally put this work online. Greenpeace are actually, they love this particular piece of work, and they've asked me to consider doing a revised version, but I don't have the time. But basically I looked at the trends in electricity consumption for what I called consumer ICT. Okay, so these are devices, mainly consumer devices. And when we did this research, we were essentially relying on data that went to about 2012. That was when we could find hard data. But we also did some predictive analysis to 2017. And back in those days, so TV panels were quite power hungry. Plasma TVs, for example, could easily use 400 kilowatts, 500 kilowatts. And that made them quite hungry devices. Today's TVs are much more efficient. Similarly, a lot of people had desktop computers back at that time, and they were quite significant amount of energy that was being consumed by everybody. Today we've seen a move away from these devices, and in fact devices have got much more efficient. Most of us rely on our smartphone for a lot of our computing, or on a laptop computer, and these devices are a lot more efficient. Now, there are also a lot more of them, and they cause energy consumption in different ways, but let's visit that in turn. Now, when we analyzed the energy from devices in 2012, we could see that about half of the energy was consumed on the device. The other energy was shared between the manufacturing, which is the purple slice of the pie there. So that's life cycle analysis. That's how much it costs to manufacture a device and eventually dispose of it. The green and the orange are interesting because these were the energies used in data centers, which we would say is the cloud, and in networks. And in fact, the fastest growing, on the right-hand side, the colors aren't very well selected, but the bottom color, is the reddish color, is actually the growth in mobile energy. And you can see that mobile energy was growing very quickly this time frame in 2012 to 2015, let's say. And it continues to grow, and in fact has increased even further. Now, the mobile energy was the communications energy from the mobile devices. So this slide shows the conclusion of what was a 150-page report. And on the left you can see, again, my 2012 analysis, which showed that half of the energy was consumed on the device. By 2017, we had estimated, and I think our estimates were broadly correct, that we would see about only 1/3 of the energy being consumed on the device. And in fact, the energy in communications and data centers has now grown to 50%, or more than 50% of the energy consumed. So today, in 2019, you could consider this trend will have continued to increase, and it's likely only 1/4 or less of the energy is actually consumed by devices. And more than half of it is actually in the cloud or in the data centers. Now, this was a very broad analysis across all devices. And again, there's a detailed report. But the trends were clear. And as part of that, we did an energy analysis. I believe the expected case was broadly where we ended up. What we did notice was that the biggest driver was the growth of 4G at this time. And the infrastructure for 4G requires a lot of energy. Now, that is addressed very much, I believe, in 5G, which is much more energy efficient. And in fact, the data rates for 5G are probably less important in the short term than improved energy of the infrastructure, the energy costs. So a lot of the energy costs arise from the use of wireless. The connections between devices and the network, most of it is actually the radio access networks. The backbone, which is often fiber optic, is quite low, and the amount of energy per bit is quite small. But the reality is the easiest way to install infrastructure is to use wireless components, and those wireless components are quite important in driving the energy budget. And I took a quick look before this talk, but I believe the prediction of around 5% annual growth has continued and continues currently. So there's a very large part of the energy consumed is in the communications networks and in the cloud storage and processing of the data. Okay. So our third point for today is that the energy and power consumption has moved away from devices and into the cloud. And this trend also means that a lot of energy consumption is actually not transparent to the end user. Now, let's switch to neural accelerators, because these are probably one of the most exciting aspects of technology in the last few years. And most of you will be aware that quite a few sectors in the ICT industry have been driven by artificial intelligence in the last few years. This started in computer vision, but it has propagated into other areas. And the reality is that well-designed artificial intelligence can solve some quite complex problems that have challenged engineers in many cases, for multiple years or even decades. So AI has been very important, but to date, most artificial intelligence has been implemented in the cloud. It's been put into data centers, and data comes from the edge and is processed and sent. The results are sent back. Now, we've seen a trend in the last few years for more of the intelligence to happen on mobile devices or peripheral infrastructure and not up in the global web services. And the most exciting part is that we're now at a point where we can put the artificial intelligence into embedded devices. So I'm going to talk a little bit about that, and then I'm going to show you what I believe is a watershed. So you may be familiar, as I don't have audience interaction, but often I ask people how many people have actually used the Movidius AI stick. So this is quite an interesting device which you can plug into something like a Raspberry Pi, and you can create literally a handheld artificial intelligence system to do proof of concept. Now, the only thing with the Movidius stick is that it's actually built inside a heatsink, so it still uses quite a lot of energy. It's working on USB 3, so it can manage 7 to 10 watts on a bad hair day, and it can actually overload the power supply of the Raspberry Pi if you're not careful in how you design things. More recently, Google has released its tensor processing unit, and this is, of course, if you're using AI, you've worked with TensorFlow. But again, a key feature of the edge tensor processing unit is that it has a heatsink, because it gets hot. And in fact, there are probably 20 or 30 startup companies who are also working to build artificial intelligence accelerators. So I've just shown one there on the side. Technically, it's not really a neural accelerator, but I like the idea. It's called a brain chip. Now, this is a board that we've played a little bit with in my research group, and it gives you an idea of what you can buy today for $20 for a development board. It has a dual RISC CPU, but most importantly, it has a dedicated video processing neural network accelerator, and also a specialized audio accelerator, which includes an FFT and hardware, which allows you to build MEL spectra and then create the audio equivalent for processing by a convolutional network. Now, what's interesting about this device is that it actually breaks the 1 teraops per watt threshold. Okay, that means you can have one 10 to the 12 processing operations per watt. Of course, the problem with these devices is although they implement the neural network in hardware, they still rely on using multipliers and similar energy-intensive equipment to implement the network. So that means 1 teraops is good, but where we really need to go, and we will see this in 2020, is we need to get beyond 50 teraops per watt. And this picture here shows a chip that I've actually seen working. It is incredibly cool. There is no heat from the chip. It, in fact, has a power budget of 25 milliwatts, which, if you think about it, is less than an LED on your board. And it is capable of running networks such as YOLO 3, which are 100 million parameter networks. So if you're working in AI, you'll be aware of people count the number of parameters. That is effectively a measure of the number of weights, of the complexity of the network. So this can perform in real time at video frame processing speeds, so 30 frames per second or 60 frames of QVGA. And it effectively provides you with data center capabilities on a chip. Okay. So in 2020, we're going to see AI being released from the cloud. Now, I'll skip over the next couple of slides, and just go to point 4 today, which is artificial intelligence is going to be freed from the cloud in 2020. There are at least a dozen startup companies working towards this aim of 50 plus tops per watt. So you will see chips hitting the market and coming into becoming available during next year. Now, having said that, let me switch back to smart cities and to the key theme of our talk today. So, I'm going to talk about cameras in smart cities for 2 reasons. First of all, because I actually know something about cameras. And secondly, because cameras are a good example of a very complex sensing system, which is a key part of any smart city infrastructure. Now, there are many other sensors that can be used inside a smart city environment, but the ideas behind camera sensing and camera technologies will help us understand how advanced artificial intelligence can help build a different type of smart city. So this case study, well, let's start with just thinking about cameras, and they can be found everywhere in smart cities. They're on the streets, in the buildings, on the roads. Cameras are very important for managing and controlling traffic and urban transportation. They're about to make their way into vehicles, and this is an engineer's perspective on a state-of-the-art driver monitoring system. Now, these are actually going to be mandated not from 2020, but from 2021 in Europe. And in fact, driver monitoring systems are a key element of the transition to fully autonomous driving. Because without a driver monitoring system, it's difficult to switch over from completely controlled by human to controlled by the computer. And if any of you have driven one of the newer cars that has advanced capabilities, including steering, you'll know that it changes your own behavior. So the key challenge the industry is running into is that people, once some of the control is taken away, they become quite inattentive. And it's difficult to know what the human is doing or to what extent the vehicle needs to control the vehicle. The computer needs to control the vehicle. So there's another example of where cameras are going to make their way into our lives. Of course, we're already being monitored in public places, especially transport hubs are important. But also now in our homes, smart speakers are now coming with cameras, and many other devices, including television sets, are likely to be equipped with cameras. It's going to have to be done sensitively, but as soon as you put a camera on the TV, it allows you to do video calls, increases the capabilities of the consumer device. And of course, people are wearing cameras as well. Now, I've worked with a number of manufacturers of AR headsets, and we can expect some new technologies to appear in this area. Again, it has been tried in the past, and there are some difficulties. I think we're going to see that. So, cameras are everywhere in the smart city. Now, in today's smart city, a lot of the data that's gathered by these cameras, in fact, ends up in the cloud. And this is a big challenge because all of that data is potentially risk to personal security. Now let's consider the effect of artificial intelligence on on cameras to build a smart camera. So the camera you have today is actually an incredibly sophisticated piece of sensing technology. It has almost perfect optics, which are squeezed into 6 millimeters, a very, very small sort of distance. But the optics are perfect and, in fact, better than in many larger devices, cameras. It includes a bare sensor array, which is a technology that is actually 40 years old. The original bare patent was in the late 1970s. But this technology is so good at mimicking the human visual system that it remains in use today, and only one company, Fuji, has actually created a different type of color filter array for image sensors. So the expertise of 30 years of image processing and signal processing has gone into improving the quality of images from bare sensors. In addition to the demosaicing, there's a whole range of other complex operations in digital signal processing that are undertaken on a camera. And this slide here shows the image processing pipeline from a typical digital camera. I originally adopted this from a US patent because it's difficult to find something with this amount of detail in the academic literature. And you know, all of these things do actually go on inside the signal processing pipeline for camera. But in addition, you get very advanced compression capabilities. The JPEG standard was a technology that was originally designed in the 1970s, and the standard has continued to be improved, and JPEG is the de facto standard for all images and image data on the internet. Okay, we can skip over this one. I just like the DCT coefficients on the right there. It's nice. In addition to still image compression, we also have incredibly advanced video coding, and most of today's mobile devices or smartphones implement these algorithms in hardware. So again, these are available with very little cost. In fact, if you look at the commoditized version of your selfie camera, so you're looking at an 8 megapixel camera on a smartphone, the mass market price for that, with all of these technologies built into the hardware, is less than $1. So if you think of the sensing capabilities that are available and the maturity of some of this, cameras are an amazing technology, but also an amazingly cheap technology. So when you consider the artificial accelerators we've just looked at, if we incorporate these neural network capabilities now into our camera module, okay, we can create an incredibly smart data analysis sensor, which can literally do a wide range of image analysis tasks on that device. Literally on less than $10 camera, you can count people, you can analyze their facial expressions. You can, to a limited extent, and bearing in mind we're not the FBI or the Identity Authority of India, so we don't want to track everybody, but we can certainly track local people on a local device, and a subset of several dozen or even 100 people is quite practical to do on a local device. We can analyze complex street scenes with different objects. Again, thinking about object frameworks like YOLO, these can provide very advanced analysis of complex scenes. And we can certainly analyze, count vehicles, look at their number plates, and do whatever analysis we need. Now, doing all of this on the camera is what I refer to as edge AI. Some people talk about mobile edge, and that's a valid proposition, but that still requires sending some data and some information up to a mobile device or to a local server. Edge AI, in its purest form, says we do the artificial intelligence, all of the data analysis, or at least a large part of it, on the device. And then you potentially take some decisions if you want to send some of that data onto a cloud service. So, point number 7 today is that the next generation of cameras with artificial intelligence engines will be able to process and analyze data at the fraction of an energy cost of a cloud AI. Because you don't have to send the data over a communications network, you don't have to send it up into a data center, you don't have to store it, and you don't have to process it on a large array of GPUs. So if we think about this capability, and we consider designing this into our new solutions, we suddenly realize that we can save a lot of energy. Now, there are still big challenges, and one of the biggest challenges is how do we deal with privacy and personal data? Okay? We can analyze and we can authenticate people on the device, but is that enough, especially in a complex smart city environment? So this is really a two-part point, because I'm going to talk a bit more about how AI engines will impact in the smart city, and then we'll return to this point and answer this question properly. So we get to the concluding part of the talk, where we actually look at reimagining how the smart city ecosystem can be built. So here's today's smart city, and we gather our data, we analyze it with conventional signal processing, but the bulk of that data, if you think in terms of cameras, the internet growth in the last decade has been very much driven by video. And it's quite common that we just send video streams, non-stop video streams up into the cloud. And that data is analyzed, and realistically, most data that goes to the cloud, it's never deleted. It's kept, it's stored, it's archived, it's moved around. 80%, 85% of data in the cloud never leaves the cloud, it just moves around from one cloud data center to another. So creating lots of video doesn't help the energy consumption of the cloud. Again, we do some artificial intelligence processing, which is typically based on large arrays of GPUs, and this is quite energy intensive. And eventually we send some instructions back to the outside world, and some control actions are implemented. The key story here is it takes a lot of energy. Now, if we think about Smart City 2.0, and we can do a lot of that processing on the edge. We can do it at very low power density. In a practical sense, it would be quite easy to power a lot of these cameras with solar cells. We don't need a lot of solar area to actually drive equivalent of a LED. So adding artificial intelligence on the edge greatly reduces power consumption on the network and on the cloud side. So we could say that this introduction of neural accelerators is going to help solve a lot of the power problems. It will reduce the data transport and data storage, and of course processing of that data if it's already been processed at the edge. If you've detected people, you've analysed their mood, if you've perhaps even identified them and authenticated them, then none of that has to happen in the cloud, and that simplifies a lot of things. We could say that in most practical use cases, you could probably reduce your energy consumption by 95%. But we still have the privacy challenge. Okay? We still have a lot of people moving around the smart city, and some of the data is invariably going to end up in the cloud. Not every camera will be capable of authenticating every person. And so we have some remaining challenges, even with AI capabilities on the edge. Now, in Europe, we're probably going to start with this approach, which is basically detect anybody in some video and just blur their faces or remove them altogether. And in fact, I know companies that are developing GDPR, Global Data Protection Regulation, friendly video cameras that basically remove all the people from the video. And if you extrapolate on that, they should also remove all the registration plates on all of the cars. They should probably not do anything inside somebody's home. And so a lot of the uses of these technologies actually gets basically chopped off by the use of this approach. But pound to a penny, this is probably what Europe will do. It doesn't solve the real problem. This I call the anonymization problem. But it does kind of protect people's privacy, but it actually destroys, as I said, a lot of the utility. There is another way to do this, and I guess smarter people, maybe in Asia, will see this as a better approach and hopefully lead the way, because it's getting difficult for us in Europe to do some of this research these days. So maybe not everybody should be anonymized. Maybe not everybody should have the right to be taken out of the video streams. Right? So if you think about it, we're kind of tracking people anyway. Almost everybody has a mobile phone these days, and that mobile device typically uses services that track our location and follow us around. And so it wouldn't be that much more of a step to actually allow us to decide that we want to be tracked and we want to be authenticated or recognized. And, this is part of being a good citizen in tomorrow's smart city. So, if you follow this way of thinking, consider you have a de-identification service, right? So I'm a good citizen. I want to be tracked. I want people to know where I'm going. And I can achieve a lot of that by using trusted third-party services, or better still, a zero-knowledge proof service where I register, and basically the knowledge of who I am is kept separate from global services. Those services will use this trusted third-party service. And you kind of have the basis of this already in India, as it happens. But I won't go into details. I'll let you guys think about how this could work. But now, if I'm allowing people to follow me around and verify that I'm me, right? And a lot of this can happen through using my smartphone as well. Then I might expect that my data is removed from a lot of services, right? So I'm allowing you to verify who I am, where I'm going, what I'm doing, but you shouldn't save that data. You shouldn't store that data because I'm a good citizen, right? So being a good citizen, I should have the right to have this data removed, and we need to verify that as well. Okay? So probably some of you are doing research into blockchain. So I think this is actually, I've lost a slide there. This is actually a good use of blockchain, because now we have a good use for public ledger technology, where removing me from the data system and the data repository needs to be verifiable. Okay? And ideally I would have control and I would be able to check that my data has been removed, but other people wouldn't. So if you think about that, now we can also then represent this in our sort of diagram form here. So you can see I've improved a little bit on the European model. A lot of the personal authentication will have to be tied in with location tracking, and that in turn will have to be linked with some form of zero knowledge proof or some trusted third party. But essentially we can now filter at the mobile edge. We can filter most of the key personal data, and any of it that proceeds into the cloud infrastructure, I should have some access rights or some control over how that is handled. So I believe this is how the mobile edge AI technology can be integrated with mobile edge to give us a new model for Smart City 2.0 that not only handles the energy aspects, but also will deal with the whole thorny issue of personal data and privacy of the individual. Okay? So for genuine privacy, and this is completing our final point there, we need to have a design which provides public accountability, and this is actually a good use for blockchain technology. I think there are a lot of people talking about blockchain, but not that many actual good use cases where the sort of the technology meets. It works well for cyber cryptocurrencies, but not so well for many other use cases. And I think that's a good point for me to stop. I think I'm just within time, and we maybe have a few minutes to take some questions. If there are questions on the far end, I would suggest somebody goes near the microphone and repeats questions. And you probably need to unmute.
Any questions, please?
I have a quick question. What is the trade-off between the AGI and the cloud-based AI?
Okay, so somebody will need to come closer to the microphone and basically repeat the question.
Okay, so see, Edge AI, you have limited information to develop the AI model. Okay, and in the cloud AI, you have a lot of information.
Okay.
So what is the trade-off when you do Edge AI versus cloud AI?
I'm not really getting this. So earlier we had somebody very close to the microphone. understand well?
So, can you hear me,
Yes.
Peter?
Yes, that is much better.
Okay. So the question is, what is the trade-off between edge AI and cloud AI?
That's a great question. And, you know, honestly, it depends on the specific use case. So there is no absolute answer. But we can certainly do advanced processes of YOLO 3 can be implemented on the accelerators. So that gives you a good ballpark, or at least next year's technology.
Okay.
Any other questions?
Any other questions?
If no other question, I'll go ahead and ask one more question to go.
Yeah, sure.
But Peter, another question related to blockchain. So you mentioned about the energy problems, right? Energy requirement, price, use, and all these things. And you are saying use of blockchain for privacy point of view, right? So the particular public blockchain, and you know public blockchain has a lot of energy requirements. So how do you think blockchain is helping privacy while taking care of the energy aspects?
That's a good point. Blockchain is potentially very energy intensive.
Right.
So I think you need to consider what's going to happen to the blockchain. And again, this is a very top level thinking at the moment, but if you consider a de-authentication service, so if I choose to move my data from public or from smart city use, as an individual, I'm not willing to pay for some of those. Then it's a solution that requires more detailed thinking and consideration than I can give in this talk.
Okay.
But it's a good question.
Okay, very good. So feel free to ask some questions. Thank you. So no questions.
Sorry. Okay, so yeah. Thanks a lot, Peter. Appreciate your time and enjoyed the talk. Thanks a lot.
Thank you. If people have further questions, the email is available. Thank you all.